Orbital 1B, radian measure, and arc length and area is what we're going to do today. Arc length. Arc length. Emily's going to read for us. Emily's going to read. For a circle.
For a circle, the radius r, a circle angle intercepts an arc with length s given by s equals, where is measured in radians. Note that if r equals 1, then s equals
Theta.
theta, and the radian measured theta equals arc length.
All right, fantastic. So this is your arc length formula. All right, so arc length is denoted by s. And s is equal to your radius times your central angle theta. However, theta always has to be in what mode? Radians. How do you convert degrees to radians? You multiply by what? Pi over 180. All right. Do you think I'm going to give you something that's degree mode and I'm going to ask for an arc length? Say yes. All right, but you're going to have to convert to what mode first? Radians. All right, so this one, we have a circle that has a radius of 4. And we need to find the length of the arc intercepted by the central angle of 240 degrees. We don't need a calculator. We don't need a calculator. Get your calculator away. What did they give it to us in? They gave us in degrees. What do we need? We need radians. So we take 240 and we multiply it by what? Pi over 180. All right. So how many radians did we have? What is 240 pi over 180 simplified to? 4 pi over 3. Good. All right. So that's how many radians we have as our intercepted arc. So now I'm ready to put it in my little formula. So now I have s is equal to my radius of 4 times my theta of 4 pi over 3. And so what do we end up getting? 16 pi over 3 inches. All right. And so that's how we find our arc length. All right. All right. Linear and angular speeds. All right. Linear speed. Emily, pick a reader. Eva's going to read. Consider.
Consider a particle moving at a constant speed along a circular arc of radius r. If s is the length of the arc traveled in time, then the linear speed v of the particle is linear speed v equals arc length over time.
All right, so linear speed. Linear speed is s over t, but what the heck is s? We just did this. Arc length. So what is arc length? R times theta. So this is really r theta over time. So linear speed is r theta over time. All right, let's keep going.
Moreover, if theta is the angle in radian measure corresponding to the arc length s, then the angular speed,
That's omega. It looks like a W.
omega, of the particle is angular speed omega equals central angle over time.
Good. All right. All right, now I need another reader for my clock. Pick somebody. Marley's got it.
The second hand of a clock is 10.2 centimeters long, as shown in figure 4.16. Find the linear speed of the tip of the second hand as it passes around the clock face.
All right, fantastic. All right, so what are we finding? We're finding linear speed. And how do we find linear speed? Arc length over time. So what's my radius? 10.2. That's my radius of my second hand. Now, what's my theta? What does the second hand of the clock do? It moves all the way around the clock, right? So how far does it travel? How far? 2 pi. Okay, it's not 360, it's 2 pi. Why is it 2 pi instead of 360? Because it's in what mode? Radian mode. Over how much time did it take? Okay, 1 minute, or I'm actually going to say 60 seconds. I'm going to say 60 seconds. All right, so we end up with 20.4 pi over 60. All right, centimeters per second. Now, what do we round to in this class? 4 decimals. Go. What do we got? 1 point. One point.
I got 1.2566.
1.0681.
All right, that's right. All right, centimeters per second. So what this means is every tick of the clock of that one that's 10.2 centimeters long is actually moving, the length of it is moving 1.0681 centimeters. All right, every time it has a little tick. All right, that's what we just did. All right, has anybody ever traveled to Indiana or something that you see a bunch of these in the Midwest? All right, does anybody know what these are?
Wind turbines.
These are wind turbines, exactly. All right, so they say it's going green, and we're going to talk about if it really is or not. All right, so I need another reader. Marley, pick somebody.
Blades of a wind turbine are 116 feet long. The propeller rotates at 15 revolutions per minute. Yeah. Find the angular speed of the propeller in radians per minute and find the linear speed of the tips of the blades.
All right, so part A, we're going to find angular speed. Well, how do we find angular speed? It's just our theta over time. It's just our theta over time. Now, what's our theta? It says it revolves 15 times per minute. So what's our theta on that one? 30 pi. How'd you get 30 pi? 15 times 2 pi, exactly. So this is actually 30 pi. That's our theta. And then how much time did it take? 60 seconds. So we're going seconds this time? All right, so let's do seconds still. All right, so it's going 30 pi over 60 seconds. So let's type that into our handy dandy calculator. I guess you could. You could do pi over 2, I guess. So it's about what? 1.5708 radians per second. All right, so that's how fast this is traveling for our angular speed. All right, part B, it says find the linear speed. Well, how do you find linear speed? R theta over time again. All right, so what's my radius? 116 feet. And then what's my theta? Still 30 pi. And then what's my time still? 60 seconds. All right. So now we're going to type that into our handy dandy calculator. So how fast does this propeller move? What is it? 2124 feet per second. All right. So we're going to find area of a sector. An area of a sector is notated by 1/2 r squared theta. Again, theta has to be in what? Radians. Now, we're going to try this again. Just like I tried to prove circumference, I'm going to try to prove this area formula to you. What's an entire circle? It's an entire circle is 2 pi, right? So if we were to substitute in 2 pi right there, you'd end up with 1/2 r squared times 2 pi. And what's 1/2 times 2? 1, right? So then this is the same thing as pi r squared. So an entire circle is what? Pi r squared. All right? So these formulas you've actually been using for a long, long time, but now you can just go straight there. All right, to whatever angle you want. As long as you're in what mode? Radians. All right, let's do one. Who looks like a golfer? Josh, you look like a golfer. Go.
A sprinkler on a golf course fairway sprays water over a distance of 70 feet and rotates through an angle of 120 degrees. Find the area of the fairway watered by the sprinkler.
All right, fantastic. All right. So we need to find the area. And area is equal to what? 1/2 r squared theta, right? But theta has to be in what mode again? Radian. So what did it give me in? Degrees. It gave it to me in degrees. So what do I need to do first? I need to turn that into radians. So my theta measure is not 120 degrees. I actually want what? I want to multiply it by pi over 180. So what theta measure do I actually want to use? 2 pi over 3. All right, that simplifies to 2 pi over 3. Now do I have all the information I need? Yes. Now we're just going to substitute in our little formula. So now we have area is equal to 1/2 my radius of 70 squared, and then times my theta of 2 pi over 3. All right. You can use a calculator. Go for it. Hey, what do we get?
5,131. I don't think that's right.
It is.
Okay, 5,131.268.
0 feet. Feet what? Feet squared. Why is it squared? Because it's area. All right. So that one sprinkler covers that many square feet. All right. So pretty good. Pretty good. So you're going to have these kind of problems on your little homework, and you're going to have an arc length and a radius, and we're having to get to this theta measure. All right. So we're just going to use our arc length formula, but we're going to kind of go backwards a little bit. All right. So how could I find this theta given this information? So what's my arc length?
75.
What's my arc length? 60. So 60 is equal to, what's my radius? 75. And then theta. So what is theta? 60 over 75. Now, what measures that? Is that 60 over 75 degrees? No, that's 60 over 75 radians. All right. Now, I want to keep going with it. I actually want to find the area of that little sector. All right, this is actually pretty cool in my opinion. All right, so we can actually find the area, not even given the central angle, if we just have these two informations. So that's pretty cool. So I'd have 1/2 my radius of what? 75. And then I'd square it. And then what's my theta now? 60 over 75. Now, what happens? We can do this without a calculator because we're really smart people. What happens? One of the 75s cancel. Isn't that cool? One of the 75s cancel. And then 60 over 2 is actually what? 30. So this is the same thing as saying 75 times 30. All right. And we can do 75 times 30 in our head. What do we get? 2,250. And then units squared would be the area. All right. So we're just manipulating. All your homework is going to ask for is that theta value. I just wanted to find the area anyway. All right. All right. Pretty good? Go. Don't get caught. Yeah, we're going to have a 2-for-1 special.